All right, welcome back to the lab. Welcome back to EE for everyone. Hopefully this sounds pretty good. I'll listen in for a second, just make sure it's working. But welcome everyone. We've got a pretty fun video today, jumping ahead a little bit in the series, and oh boy, is there a story around that. So we're going to be talking about the DMX project, specifically zeroing in on one of these quadrants of the board, one group of these LED drivers. All right, the audio is coming back through on the stream. All right, turn it down a little bit. Hopefully that's better. All right, I can't talk while I listen to myself, so I got to take this off. Let me know in the comments if something is broken. Oh, excellent. Okay, so the first thing we're going to need to do is tack on some wires. We've got the soldering iron here, and we need to hook into the control lines for one of these parts. Wait a minute now. Yeah, that's right. Cool. Excellent. So, yeah, it'll be a pretty quick setup here. I suppose to walk you through the whole thing, we have the power supply over here to power on the board. We've got the function generator to manually drive this. Will be controlled by a DAC. We're going to talk about all this in a future video. But basically, there's some DACs here that aren't on the board. We're going to override that and drive the control lines directly with a couple wires and the function generator. I was just getting it set up. Oh, the camera disconnected. Sad. There we go. I was getting it set up, just confirming the voltage level was correct, not exceeding the 5 volts the system can handle. So we'll be walking through the setup test, and we're going to have some fun because this is well, it's not a very good design. It was quite a rush. The whole story is going to be awesome, coming out in a video very, very soon. Until then, we'll cover some of the highlights today. In another fun twist of this adventure, we no longer have serial number 1, which was the only board that's fully functional, which is kind of funny. Okay. All right, there we go. All right, I think I'm going to need to pull up the design files because tacking onto those tiny wires is going to be a real treat. Hello, Dave. Welcome. Welcome to the stream. For those watching, there may or may not be fun alerts when certain things happen. Testing out Streamlabs today. I forget what all works. I think folks subscribing, becoming a channel member, super chatting, those 3 actions should do something on the stream. We'll see if that works. I have no idea. Basically, one of my friends streams on Twitch, and I saw his stream, and I was like, man, that looks awesome. It's just a fun way to interact visually with everyone and like put your name on the stream. It's pretty cool. So just thought we'd give it a try. Okay, sorry, getting the schematic pulled up. Unfortunately, I only have 1 monitor today. But other than that, I think we're pretty well set. Okay, I don't know. What are you guys feeling today? Channel 1, Channel 2, Channel 3, Channel 4? All of them work, I think. So they should all be fine. Channel 2 is kind of right in front of me, so I'm inclined to go for Channel 2. No votes, then I'm going for channel 2. J. Oh, wait, there's a delay. Alright, I'll wait a second. I believe that's J402. Okay. Schematics and all that nonsense. Coming soon. I suppose I could post that. That'd be a good idea. Okay, I'll put a Google Drive link together. One moment. Yeah, it's a lot more fun when you can follow along, eh? So yeah, this design is coming out very soon. Looking for 2106. It's not there. Right on. Well, we'll add it. Get a link. Okay, it's coming in chat momentarily. Dave, that's sad to hear. I tried to schedule this stream yesterday. Let's see if I can pin this. There we go. So anyone logging into the stream should be able to find that. In theory, it's a link to the schematic we're talking about today. I'm on page 4. Yeah. So J402 looks like the control lines for that one are going to be pin 2, 6, 9, and 13. That is really what I was looking for. We're going to tack on wires to pin 2, 6, 9, and 13 of this part. All right. First things first. Identifying pin 1. Okay, there it is. So it means I'm working on the other side of the part. Pin 2. Whoo. Alright. Got that one with some fresh solder on it. 2, 6. Seems like 6. 9 and 13. 6, 7, 8, 9. I gotta clean off soldering iron. 2, 3, 4, 5, 6, 7, 8, 9. Ah. I love symmetrical parts. Yeah, I don't know how people get notified of streams and such on YouTube, but I'll be the first to admit we've been a little less regular than usual in our everything, but it's all for good reasons. Honestly, there's not much to complain about for me at the moment. But yeah, I don't know. YouTube tends to not show stuff when the channel's not as active, so it could be as simple as that. But there is the bell thing. I don't know how into YouTube you are at the moment, but there's a bell, and you can select which notifications you want to get. I've heard that periodically it'll like reset that, so you might need to resubscribe to notifications for EE for everyone. It's I know it's a little frustrating, but that's what they're doing. Okay, so what I'm doing is I'm just going through. What? Making sure I've tinned to the right pads. I'm sorry, what? I was expecting Some continuity beeps. Oh, okay, there's one. Okay. Checking the deck control lines. Okay. Why is that one not? Okay, there we go. All right. So looks like we got the right pins. Those are the ones coming back to the deck. This is going to be really cool. Okay, so a little bit of story time. By the way, just welcome to those watching. I don't know if I can see a list. I really don't know if I can see a list. All right, so I'm going to see if this thing works. So allegedly, if somebody were not subscribed and subscribed, it would do that. And I had way too much fun. I've been learning how to make animations. That's been super fun. And it was just cool to take our logo and light it up. Yeah, Dave, I'm not too surprised about the alerts thing. Seems like the latency is a little more than it used to be. I don't know. If someone wants to send a very obvious test comment or chat or whatever they call it these days, just like do like a start stopwatch. I'll read it off as soon as I see it. And I don't know. I feel like it's like 30 to 40 seconds right now, which seems a little bit longer. Okay, cool. But so now we know our pins. We need to tack this on, and story time. So the story. Basically, there are some timestamps related to this project that I'm not super happy about. I started this project quite a while ago, and I believe this came out in the final edit, but a big part of why is because I was actually helping someone out. Like, they had a real need for something in an amount of time, and I was like, yeah, I can do that. And so we kind of surged ahead in the progress in a way that I usually don't do. Usually keep them a little closer to synchronized. And so, yeah, we're just capturing the whole story, and I can't wait to tell you all about it. But I suppose, it would be pretty normal. I would say it'd be pretty usual for us to share some information with the folks that are able to watch the live stream. Just, it's kind of what you get when you come for the raw, unedited goodness. You get the raw, unedited goodness. And so, yeah, basically, the board that we're testing today is not the final revision of this design. Not even close. It's there's at least one more revision, but there's been some recent developments, which I don't want to get too far ahead in the story, but there's some things that I discovered that I forgot in the second spin of this board that might warrant a third spin. So it's really cool because, it's one thing to look at a textbook and hear the do this, don't do this, this is good practice, here's how electronics work, like an electronics design course. That's pretty common in university. But to actually see a circuit board not work or have a black mark on the PCB and or have a component go nuclear because you were rushing and forgot to do one of those best practices just really brings it to life. It gives a solid example of, yes, this is exactly why we must listen to those textbooks. Some of those are more guidelines than rules, and some of them are more rules than guidelines. Like, for example, fuses. More a rule than a guideline. I don't know what the limit is everywhere, but in general, I believe it's if you have more than 15 watts flowing through something, you need to have a fuse to prevent it from lighting on fire in the event of a catastrophic failure. Because these things happen, right? You put electronics in the world, they're used for 20, 30, 40, 50 years, and Stuff breaks. Oh, I haven't looked at chat in a while. Hopefully nobody did that stopwatch thing. Nope. Oh, yeah. But at any rate, feels good to be back on stream. Feels good to be talking with you guys again. Feel free to let me know if anything's not right with the audio or video or the stream or anything. But I did I won't say great job, but I'd say about a usual job of getting things set up. Okay, so here's where it gets fun. I'm going to switch to the picture-in-picture view. Looks like it's cropped off the bottom. Huh. Okay, yep. There we go. Live edits. Love it. Okay. I'll try to keep things on the screen considering that. Okay. So we've got this cool not USB LED panel. This is one of the things I'm hoping to use this driver for, or something similar. And oh yeah, I suppose I could walk you around the board before we get too ahead of ourselves here. So the board itself, this is one of the Rev-A Protos, and it has a few things. So it's got the screw terminal input. It's got 4 fuses, 1 per LED strip, because of course more than 15 watts going off to wherever. So you need to make sure you have an appropriate fuse that will blow if there's an event of a catastrophic failure, though I don't know. It really depends, right? You don't know how much power is leaving, and that's a common problem, right? You look at any LED tape driver, they don't know how much LED tape you're going to connect. So I don't know. Maybe that's like I won't get into the details there, but I feel like there's something going on, some important nuance that should not be missed. So this is basically running every channel, or it attempts to run every channel as an LDO. And many of you are very familiar with the traditional LDO arrangement. Let's see. I can probably use this piece of paper here. Sure. So in the traditional LDO arrangement, you have your op amp. You have a pass element. In this case, I'm drawing a transistor. And then you got some kind of voltage source that is being regulated by that. You have your V out, which goes to a load, an RL. All of this is referenced to ground. And you have some sort of feedback network which allows your op amp to regulate with some kind of a reference. In this case, I'll draw Zener reference. All this comes down, and yeah, you have a pretty typical topical, sorry for the sloppy handwriting, and some of those resistor squiggles are a little small. All of you European viewers, if you're awake, yeah, you ought to be awake at this time. Sunday morning for you? Saturday? No, Saturday for me. I don't know. Night? Whatever. I could look it up. That's something you think about every day. But, so you get your voltage source, your voltage output. It's regulated here with your reference and your series pass element. But let's think for a minute, right? That doesn't really work for this application because... Excellent, Dave. I'm glad to hear the video and audio are coming through great. So here, what we have is we have an RGBW strip. So I'll simplify this, and we'll just draw a diode for each one. And they have a resistor. And in this case, they're electrically connected common anode. So the positive side of all these LEDs is tied together. Yikes. Let's think about this circuit for a typical LDO. It can pass current only from the voltage source to the load. It cannot sink current in this most simple configuration. Well, I'll give you a hint. This is a quad channel op amp. Those are four, they're transistors. They're not FETs, they're transistors. These are 4 transistors that are functioning as the pass element. But since we know this configuration, you just have a, what would it be? I think it'd be a PNP transistor and a PMOS FET in this configuration. Oh, sorry, got off screen a little in this, the way I've drawn this. So you know we didn't make this circuit, because if you connected one of those to each of these lines, as we did, nothing would happen. Okay, so what do we need to do? Well, we basically need an NMOS or an NPN transistor with a control line. I'll just draw a generic op amp there. And some kind of feedback. And what you end up with is an awful circuit that doesn't work. Because the gain is so high. Because this is a voltage controlled device. This is a current controlled device. Okay, so you add a resistor. And then you still end up with an HFE or an effective gain, a current gain. And now, depending on how many LEDs you have, that current gain will turn into a different amount of voltage gain. So you have this widely varying gain. And we're going to talk about this a lot in our next video. It's almost ready to come out. It's coming out very soon. Basically, we saw this, and I ran a simulation in LT-Spice, and it wasn't stable. It was oscillatory. The system didn't work. And I was like, you know what? I'll figure that out. I'll figure out that instability. I'll find a way. I'll find a way to figure that out. We'll just order the fabs. We'll get them. It kind of sort of works, except for sometimes. But that's the kind of thing that you just can't. Like for me, to demonstrate the principle in a video, sure, whatever, fine, okay. But when you want to hand it to someone and just have it work, way too flaky. But thankfully, half of my reasoning when I did this awful, awful decision was correct. The second half of that thought process was, well, even if it totally blows up and it doesn't work at all, at least we'll get to talk about it on YouTube, learn some things, just do something that you shouldn't do, and then learn from it. One of my solder joints broke. Just need to reheat it. Oh yeah, so that's the backstory. Don't judge me too hard for this one. I'll freely admit it's not great. So it's always truly and sincerely meant, but the warning on all of our schematics that says this is for educational purposes only, yeah, take that one extra seriously this time, because it straight up does not work. Thankfully, there's a Rev B. We'll have an opportunity to correct our mistakes. All right. So, with that out of the way, let's connect our light. Find a way to get that framed up. Yeah, it looks great. Looks like I have green going to the 12 volt input. Got to get our EE for everyone toolkit. Definitely not just a sticker on a standard one. Yeah. And we need a flathead. Looks like a 3 mil. Oh yeah, that's perfect, like a glove. Excellent. So yeah, I mean, it's weird because I kind of love and kind of hate where this ended up. Like this rev. I'm not talking about the whole project. I'm talking about this revision of the hardware. I love that it works because it really, really shouldn't, like at all. it should not work at all. So I kind of love, like, when we power this on, you're going to see, to the human eye and to a camera, I really don't think it's going to flicker. Oh, no, I need to go find a fuse or this thing's not going to turn on. Yeah. Sure. Easy. Okay. Yeah, so, sorry. Getting distracted by trying to screw in a screw terminal. That shouldn't be the hard part. It's just the wires are really small, so they were slipping out. So, yeah, I don't know. I guess seems like a few people are dropping in, and thank you all for watching. I don't know if any of the alerts have been going off, but usually it'll play a little sound to let me know to look at things. Hopefully we get at least one before the stream's done. That'd be cool. So, yes. But sorry, I got distracted again. This happens. So the LEDs do light up. The controller kind of works. But my biggest gripe with this whole arrangement, my biggest gripe with everything about how this works is, like, it's so bad. Like, it's almost comically, like, you would think that I intentionally screwed this up because of how bad it is. Maybe I just set my standards too high. But, like, there are big, fundamental issues with this control scheme. Not the least of which is the intended application. Light control. Right? If you want to control lights, you want them to be a color, a predictable color, a repeatable color. And when you're driving LEDs, many of you probably know this, but they have different forward voltages, right? So your blue LEDs and your red LEDs and your green LEDs all have different forward voltages. So if you set all of these channels to a particular voltage, it's like if you were to make it what should be white, right? Like all full brightness, just go for it. You're going to see white. If you turn it all the way off, you're going to see black. And everywhere in the middle, you will see this spectrum of colors as the different forward voltages are exceeded. It's not going to be white all the way through. So, like, what's even the point? Even if this worked, it is, like, fundamentally flawed in a way that I find kind of hilarious. Okay. So I want to look at the LDO first, just to make sure that powered on, or the switch mode power supply. Got a simple 5-volt buck. I believe you've seen this one before. It's a... there's no part number on it because it's too tiny, but it's a Texas Instruments very, very basic switcher. It is just about as simple as a switcher can get. And sure enough, looks like... Oh, sorry, I usually have a dewarp filter, but Streamlabs OBS, I need to get all that stuff hooked up again, so it's a little fisheye distorted, and apparently there's some glare. Let's see if I can fix that. Is that better? Yeah, not really. Well, okay. Okay, I'll just shield it with my hand. But, so yeah, you can see the switcher there. I've got it DC coupled. Let's AC couple channel 2, and then I'll zoom in a whole bunch, and we'll take a look at the ripple as well as we can without... oh, I've got another contentious thing to say. Okay, yeah, so there's a fair bit of noise, but my ground loop is huge. You really can't measure ripple with this big of a ground loop. I mean, it's not switching noise, it's just noise. That could be coming from the power supply coming in, could be from lots and lots of things, but okay. So let's switch this up. I'm going to put this on the blue channel, We're going to go back to DC coupling. Oh, okay. DC coupling. Gonna put that on 5 volts per division. We have a 12 volt input. So my expectation would be to see something between 12 volts and ground. And we need a fuse, which I have. Okay. Fuse. Sorry, I meant to be picture-in-picture there. Okay, so we have the fuse. I'm going to plop that in. That might change things. Why did only green turn on? What? What? Well, I mean, EE for everyone green. I mean, I love it. But, like... What? Oh, no. Wires are breaking off. Oh, no. Well, that probably has something to do with it. I guess that's what I get for soldering straight bare wires to this thing without any real controls. Okay. So I'm going to figure out which one of these control lines is modulating green. Also, I'm going to connect this to the green signal wire. Should be this yellow wire right there. Excellent. And of course, I'm behind the screenshot. I'll just show you the whole thing. Okay, so this seems reasonable. The blue trace should be showing us the output voltage. Since the 12 volt line is 12 volts, 0 volts would be ground. And now, in theory, if I've tacked on wires correctly... Oh no, it's all over the place. Sorry, took off the ground clip. So now, in theory, if I do connect this control line... What is happening? Oh, it's because they're floating. Oh, that's cool. You can see the sinusoidal modulation. Oh, fun. That one doesn't seem to be green. So is this one green? Okay, apparently the green channel is real broke. Okay, well, we can fix that. We can use blue. We'll just take this. We'll get on the blue channel. What is happening? How are we getting a negative voltage? Oh, I've inverted it. Haha. Invert. Ah, man, I was freaking out. Oh. Can you see solder under? I didn't leave that solder draping over there. Thankfully, it was just under the heatsink. Thankfully, yeah, this is just a little heatsink on the LEDs. So thankfully, I didn't blow anything up. Yeah. Oh, WTP Gaming, that is a fair thing. Yeah, so, yeah, I suppose, yeah, you guys are all gathered here. May as well so I haven't been working on this the whole time, but, you know, there's a lot that goes on in a person's life, and there's been a few multiple factors going on, not the least of which is trying to carve out a little bit more time for family. I mean, I think we all know it. The last year hasn't been the best for, like, seeing people. And so there's a lot of people that just need to take some time and reconnect with, really. And it's been an awesome thing. Obviously, I miss doing more stuff on Eat You For Everyone. So that's part of why we're here, getting back into it, kicking things off properly with a good hangout. But, you know, I was just taking some time to prioritize other things. And got to do that every now and again. But I'm excited to get back into it. So, yeah, it was like solved the problem for my friend, and then, oh boy, what is happening here? I need to slow this down. I can't make sense of that because the scope refresh rate is real slow. So channel 1, we have in 2 volts per division. Frequency. Oh, there we go. This will be a lot easier to see. Got it down to a 1/10 of a hertz. So, yeah, no, but there's some really cool stuff in this project. Like, can you guys see when those lights turn on well? I've got a focus assist thing, so I can't. Everything looks blue to me all the time. Yeah, it's not super obvious. Let's see. If I turn this off, how? Well, you can't see anything except for the lights now. We'll turn them back on in a second. But okay, this is highlighting everything I wanted you to see. Okay, so I'm gonna try to gesture at the scope. It'll be hard to do that without something that's lit up. You can't really see my hand. Can you see this bright red thing? Nope, just looks black. Okay. Well, on the yellow trace, you can see that critical threshold where the lights really start to turn on. It's just the output's hanging out at very, very close. Very, very close to the threshold voltage of the LEDs. And it just sits there, passes a few milliamps of current through. Never quite turns off. And then as the voltage continues to increase on that control pin, it gets brighter. So what I'm seeing is our offset voltage is not correct. I need to try to get that down to actually 0 volts. Our control line is not getting low enough. I have a feeling that's because of the 50 ohm output. Oh yeah, that's brighter. So open circuit, we're driving to negative half a volt at the lowest, but it doesn't seem like, oh no, what just happened? Oh, that ranging scared me. Whoo, that is getting bright. I think that's bright enough that we can see it with the lights on. Oh, okay. So let's just double check the control voltage. The reason why I'm doing this, someone might say, well, the scope's good enough, isn't it? Well, kinda. It's kinda good enough. But it's not really calibrated for DC. It's calibrated for AC. So when you get down into the range of a few tenths of millivolts, you might start to see some problems. Yep, it looks like we're getting down to about 0.6 volts. All right, let's see if we're getting down to 0 now. Seeing 400 millivolts. That might be as low as we can really get. Oh, we got down to 100 millivolts. That's pretty good. That's pretty good. So now we're using the full range of this controller. So if our DAC were connected, that'd probably be about where we'd land. And now what I'm hoping to see is on the blue trace, I'm hoping to see that get really, really close to ground. And it does. I'll be bold. I'll bring this down a couple more. We can drive it with about negative 0.3 volts, and that won't be a problem. So we'll do one better than our DAC can, and we'll get it even closer down to ground then. Yeah, there we go. It's a couple millivolts below ground. Cool. So that's kind of the principle of what we're going on here, and what we have going on here, and there's that issue of never turning off is another really big issue, right? Let's let me see if I can share the PDF without breaking everything. This is danger. I'll only do it for a second. But okay. So I need to make a new source. Window. What do I want to do here? Well, I want to demonstrate this instability because I have seen it on the scope. I know that this is unstable, and I want to prove it. Right now, this looks too good. This looks too clean. It looks too correct. And I think a part of the reason why is because our power supply is masking the issue. You see all that noise on the scope? Well, let's grab the linear supply. Let's swap this in, and let's see if we can really demonstrate that issue. Yeah. Ignores danger. All right, let's see. Loopsy loops. Assuming the circuit works, how many amps can it handle? PWM driven. What is the maximum power it can handle? Whoops, it said danger, my guy. No audio. What? Is it back? No? Hello? Oh, I added a new window without audio. Testing 1 2. I cannot change settings while I'm live. Is it back? All right, let me get on my stream monitoring thing. I didn't adjust this. Okay. Yeah, I monitored the stream. We're back. We're good. Okay, I will go back to the window and so what said danger? There we go. Now you can hear me on the PDF. Yeah. Okay. Cool. So what I was saying. Sorry about that. What I was saying is I only have one screen, so I couldn't see the comments while I was on here. What I was saying is one of the major problems is that with this B2, we're looking at the blue channel, right? And so at the blue channel, then you have this feedback network that passes a minimum amount of current through the LEDs, which is why they never turn off. It literally cannot turn off the LEDs because that small amount of current is enough to barely illuminate every LED in the entire strip. So in a lit room, like right now, right, we got the lights on, you can't really tell. But in a dark room, well, that is just about the most obvious thing you can have. And then, of course, the op-amp can decide to turn that down. So what I'm hoping to do is demonstrate the instability of the system, right? I'm hoping to really demonstrate what is going wrong here. And, oh, yeah. Yep. That's fair enough. I'm like, modifying the stream setup live. That's not just generally not good. And, notifications pop up and all that good stuff. It's like, I have no idea what you're going to see. Well, let's do it anyway. I wanted to show you the schematic. So yeah, we're going to try the linear supply, which should get some of the noise out of that measurement. And, yeah. So yeah, this design has a lot of problems. I picked it for silly reasons. Uh-oh, something disconnected. I have a feeling it was the scope camera. Seems to get grumpy with me whenever I touch anything on the bench. Okay. So now we got the linear supply in here. Good stuff. We got it set to 12 volts. Current limit is reasonable. Let's power on. Oh boy. That's a little different. Hey, do you see all that weird flashing happening now? That's pretty weird. What was that about? I wish I could have seen the scope. We're going to keep that picture-in-picture view going just fine. Okay. All right. I'm going to deactivate, activate. There we go. Yeah, that was really goofy. Let's see. I'll scooch this a little bit, and then we'll expand that a little. Excellent. So, I wish I could see the list. That's pretty cool. WTB Gaming, that sounds pretty sweet. Wireless DMX, huh? What did you use for the transceiver on the wireless side? Did you use something standard or like, Wi-Fi, Bluetooth, something like that, Zigbee? Or did you use like one of those bare like RF modules? Yeah. I don't know what it is about DMX compatible equipment, but it seems to be either like super, super basic or pretty expensive. What is happening right now? Scope. What? What are you doing? Okay, there we go. What was that weird glitch on power up? Let's try that again. Oh, probably because I was driving the op amp when it was powered off, and it was probably really upset about that. Yeah, that's a thing you shouldn't do. Thankfully, this one seems pretty rugged in the sense that it's not dead. But yeah, those protection diodes are getting tested. Oh, that'd be fun. Oh, yeah, okay. So, Insider, let me catch you up. Uh, so, um, so this design is awful. We pinned a comment in the schematic, and I'm just highlighting all of the issues that I found with this board. So we're in the middle of a series talking about a lot of things, but generally talking about the DMX protocol, talking about LED drivers, talking about just a lot of things. And this board that you see here is a perfect example of going too fast and blowing stuff up, or going too fast and building something that doesn't really do what you wanted it to do. I went from in a hurry to reckless with this project. And this is a great example of what happens when you're reckless instead of taking your time to design it right the first time. So in our series, just going to take some time to recognize kind of the thought process, the incorrect thinking that led me to build this monstrosity. And then the second rev is, well, still a lot bigger than WTP Gaming's DMX driver, though mine does actually have 1.5 kilovolt isolation on the DMX interface, so I don't know, I'm just saying, add some space. So it's basically it's got a PWM controlled thing, because I'll just highlight some of the things that immediately come to mind. So on this old board, the way that we designed what is functionally an LDO, this is functionally a linear regulator, but we put it kind of upside down and backwards. It made it quasi-stable or unstable in some situations. I think either light load or heavy load, probably light load is worse than heavy load. And I was just swapping out the power supply. You can see the voltage waveform is a lot cleaner. So when you start to see some oscillation, I think right now it's actually pretty tame, but I think it is there. Let me zoom in a touch. I think there is some high frequency stuff going on. We'll do mode. You did trigger. Source 2. Rising. What is happening? So hopefully that answers your question. I just changed the trigger source and it didn't change the color of the trigger source. What is happening? Can we get you to just... How's the auto trigger not going? Okay. Coming back to the comments here. Okay, look at this. Yeah, so I did a bad thing to finish off that first comment. I did a bad thing. I'm owning it. I am saying this was bad, and I did bad, and I feel bad for it. But hopefully, as long as I've already made the mistake, I'll just eat my piece of humble pie and, yeah, just share it with you so you can see. So yeah, what I was talking about with the isolation is this isolation domain here. There's a power module that gets the 5 volts across to the other half of the RS-45 driver, and that just helps to avoid ground loops and some other things in very large systems, like in a theater where you have 20 to 120 lights kind of chained together on the same interface. Leakage current can add up, and it can start to be a problem. So yes, this is where we're headed. This is where we are today. Cool. Sorry, I repeated it twice. You probably... Oh, sorry about that. I'm going in circles. But yeah, so an ESP12F, few off-the-shelf FETs. What frequency did you do your PWM at? Because, yeah, this one's PWM too, because heat. That's one I keep forgetting to mention, heat. That's why this board's so big, so I can plunk one of these giant aluminum heat sinks on top. When you start to pull 2 amps per channel, which is what this is, it's intrinsically current limited. There's a maximum amount of base current that you can get into the transistor the way that I've designed it, and that limits the amount of current you can pull down. But if you start pulling that current, you're dropping a significant voltage on these parts. You know, when you start burning integer watts, 2, 3, 4, 5, 10 watts, they get hot. You need a big heat sink to get all that heat out. So compare that to these absolutely tiny transistors that can handle the same power and do much better with color accuracy and dimming, and it's cheaper, takes less board space, easier to lay out, less component, literally better in every way. I just needed to get over the fact that it was PWM. Yeah, that WTP gaming, that sounds awesome. That'd be really cool. I've thought about doing like a highlight, like highlighting some of our awesome projects happening like in the community, because you know, one person can only do so much, and I think that would be probably copying a little bit. Okay, so I'm going to swap this out. I've got a small test LED strip. This one is much lighter load, so just thinking realistically, this has a lot more LEDs. So our current-based system will have a much smaller voltage gain because you need to pull more current to change the voltage. This will fly around like nothing. It's like the minimum load you can have. So let's swap that in and see how different these waveforms look. Well, I keep chit-chatting. Oh, yes. So, yes, if anyone is watching and is not subscribed, I believe you have an opportunity to make an alert pop up on the screen, which would make me giggle and also smile. I won't even say you need to stay subscribed. I just want to see if the alert triggers from someone else doing it. Someone else other than like the tester. Okay. Disconnected. Yeah. So it's a pretty cool project, and yeah, I suppose we have been talking about DMX in this project for quite a long time. It's been nice to slow down. Like, this is something where depending on when, by the way, never do this when it's powered. I should probably turn it off, hey. Okay, so I'm turning off this function generator first to not drive the board, and then I'm powering off the power supply. That is the correct order. So we used to do a lot more of this slower content. Like, we used to do a lot more of the more educational, like more textbooky type, like theory, circuit theory, component theory, like the DMX video, where we just took a moment and talked about DMX, what it is, what it does, made some animations, spent way too much time making some animations. Yeah. That type of content, we used to make a lot more of it, but I was a lot worse at making videos back then. I don't know, I kind of like bringing textbooks and theory to life, so it's like, yeah, we've been talking about this project for a while, but also, we haven't really been talking about schematic design. We haven't really been talking about, like, the design process, really. We're, 4 videos into the series and 3 videos in? I think we're about to be 4 videos in, and that's going to be the first one that really talks about designing this board. I think it'll really fly after that. Probably a couple more videos, live stream. Maybe, yeah, something showing off the controller software we used or something. I don't know. It's just some free stuff on the internet. But yeah, I think we'll get through this pretty quick, and I'm excited for the next project as well. Okay, what is happening now? Ooh! Oh, sorry, I got too excited. Oh no! It looks like one of the pads is breaking off. Okay, there we go. Oh yes. Oh yes, you can see it. Oh, you can see it now. Okay. Switching to the Do you see that? Do you see that AC oscillation? So the drift. Okay, so this is AC coupled. So you have to keep in mind the two signals and what we're seeing. These came from Express PCB. No, not Express PCB. That's sorry. I used to use them. These are from JLC PCB. So these were done, assembled by them. They did a pretty good job. Yeah, So, I mean, this is something where production is very different than building one board for yourself, right? If you're building a board to sell in a product, you want to make sure it's UL 94V0 rated. You want to make sure they have good process controls and this and that. But for me, doing something like this, I'm really just using them to save some time. Putting down all these passives, using their pick-and-place machine is great. I mean, for a one-off prototype, it is super cheap and quick, at least a lot cheaper than my perception of value around my time. But yeah, I mean, definitely do your own homework. There's a lot of good fab houses, but yeah, they did good work. Okay, so I want to try to. Oh, hello. Oh, there we go. I'm going to try to move the 12 volt thing is breaking a touch, so I'm slowly scooting the LED strip down. Okay, there we are. So the blue is on, and now you can see that same leakage current. The green was probably barely on before. Oh no, the green was stuck on. The green was stuck on. Yeah. Okay, so let's see if we can really capture. Triggered at channel 2. Zoom in vertically. Zoom in horizontally. Try to capture what frequency. Oh, did you see that sinusoidal oscillation? There was an unstable set point. I don't know why I'm singing. That was way too exciting. Yeah, there's some baby oscillation. There's some big oscillation. I'm showing you this, right? Yeah. Ooh. Yeah, so that's what this circuit does. That's what this circuit does at some set points. This is what I was hoping to demonstrate for you today. Yeah, that's not good. Let's see if I can get the. Oh, there's that one moment where it's like constant amplitude. Let's see if I can find it. I don't know if I'll be able to trigger on that. It's tricky because it's. Oh, wait, I know what I can do. What am I doing? I will just turn this off. I can go to a DC waveform. I can go to the DC modulation. And we'll go to the. I don't think the offset does anything now. Okay, let's turn that on. What? Okay, there we go. Ha. Yeah, 0.1 volts in. That's a pretty sine wave. Let's get a frequency measurement on that. Yeah. Sits at about 500 kilohertz. Cool. Oh, that's cool. What do you guys think about that? How are you going to damp it? Well, I suppose, yeah, we could try. So, I've got an LT Spice sim, and I'd love to do this live with you, but unfortunately I do not have a supercomputer. It takes forever to run these simulations because it's not very stable. So, by the way, welcome, Muhammad. It has been a long time since we've talked. But I believe you're here for our last live stream, and if I remember correctly, it is way too late where you are when I stream in the morning. So, my apologies to keep you up so late. But I'm glad you're here. So we have a couple options for how to damp it. First of all, this is an extreme light load condition. If we just add a bigger load, the problem goes away because the voltage to current translation, like the effective resistance, gets larger. The real way to fix it is to do PWM, which is what I'm guessing WTP Gaming did. I didn't mention 5 amps. That'd be cool. I mean, we'll gladly check it out. I love being wrong and worse. Yeah, actually, I have a P.O. box. Ooh, I have a P.O. box. Yes. Do you have an email on your... Okay, so WTP Gaming, do me a favor. If you send me an email, if you go to our YouTube page, like youtube.com/c/EE for everyone, go into the About section. There is a inquiry email, like a business inquiry email in there. Publicly available. Just shoot me a note on there. I will make sure that it's you. I'll send you the P.O. box. Yeah, I would love to check that out because it's probably a lot better than this. And I do have a DMX transceiver, so I should be able to interface with it. Yeah, that'd be cool. That'd be cool to see. Hook it up to the scope. So anyways, getting back to the point here. How do we damp it? Well, we can do two things. We can adjust the circuit. Let's switch back to the circuit. We can adjust this circuit. If we change the resistances, the capacitance, and if we change that gate drive resistor value, we can adjust the gain of the system. And just like any other control system, if you adjust the gain, just simple stability like gain margin, phase margin. Oh, I might need to explain that. Let me know if you want me to explain that. I'll need to take a break for a second to go find a piece of paper, but I'll come back and I'll explain that. And I've also got a Sharpie, so you'll be able to see it better. If you want me to draw a quick thing on how that works. Basically, we don't have very much gain margin right now. We have some phase margin, but we have very little gain margin at some operating points. And some might say, like, yeah, you know, this isn't great, and yeah, it's not great. You know, we really should do a little better than this. But I'm wondering, there might be a set point with even larger oscillation. Let's see. I'm going to jump back into the tenths. Now it's getting smaller. This channel is working pretty well. So yeah, it really does seem like that is the maximum point. But there's a bigger problem here. Were you listening to the amount of variables I just listed off that affect the stability of the system? It's going to be very difficult, if not impossible, to guarantee this is stable in all conditions, just because of the nature of this design. The component tolerance on those resistors, the component tolerance on the capacitor. So here's what I'll do. I won't totally cop out. I will, this one's blue, there's the resistor, there's the cap. I can see the feed forward cap. I'm going to mess with that cap. What? Oh, no. No email there. Well, should I be bold and just drop it in chat? Spam City? Spam City? Let me check. YouTube.com/CE for everyone. Oh, it's going to start playing stuff. Hopefully that's muted. About. Yes. So underneath the description, it says for business inquiries, view email address. You click that, and then it probably does a reCAPTCHA silly thing. And then there it is. It is on that page. If it's not there for you, I'm confused. It's under details. Description on top, then details. Yeah, very cool. Yeah, I don't know. They used to be able to just like DM people. Like, you guys remember that when you could just direct message people on YouTube? That was great. Like, I literally cannot send people a message. Like, I can't message you and you cannot message me unless you have linked an email. If you have an email linked to your account, I can get it there too. That's fine. But okay, anyways, I'm going to mess with that capacitor and see what happens. Let's see what I got here. I got the mics, the 10th mics. I may or may not have moved to the shop yet again. But we do have a lot more space now, which is really cool. So these are not puffs. These are microfarads. So I need the big one. Okay. That one's empty. Oh, no. Where's all of our picofarads? Oh, there they are. There we go. We got the picofarad slide. So this is something we did on the channel a long, long time ago. So what were we? I think we were at 100 pico before. So I can put down we can do another. We can double it. That seems not totally ridiculous. I need one of those nice fine tweezers. Right on. Here we go. So this should have an effect, either increasing or decreasing stability, and or moving that point around. Oh no. I may need to solder this into circuit, but I want to have an A-B comparison. Alright, I think I need to solder it in. But then just for fun, we'll grab 1,000 pico as well. So we'll tweak it, come back to the exact same operating point. And then we will... okay. Got 1,000 and 100 pico. Powered down. Grab the soldering iron. Will it? Yeah, so I know that having too little capacitance or too much capacitance will very, very severely affect the stability of the system. In fact, I'll put my money where my mouth is on that. I will take that feed-forward cap completely out of the circuit. Okay, let's power on. Let's turn on the input. Yeah, there's a little more instability. And now we're not even getting simple frequencies at this set point. I think we're getting like AM modulated noise. Oh, yes, that is good. Even less stable. Love it. So we have this high frequency component, which is now at 200 kilohertz. But I'm guessing if we adjust the set points, there will probably be ranges. We're doing hundredths of volts adjustments right now. And we are we're at 500 millivolts per division. So there are times where this noise is greater than a volt peak to peak. So that's almost 10% ripple or 10% noise. That's not good. This would be an EMC nightmare. Okay, so that was too little capacitance. Seems to be about the biggest we can get it. I'm going to add too much capacitance now. A big resistor in parallel with the LEDs. Yes. So putting a resistor in parallel with the LEDs is a fantastic way to get rid of that that glow. That will absolutely fix that. And it will define a minimum load level. So yes, both of those things will help to improve stability. Yes, those are great suggestions. So yeah, I'm pretty confident that having a super high gain is one of the primary factors of the why this is super unstable. But I wouldn't be surprised if there were some more nuanced reasons why this circuit has fallen out of favor. A great place to look would be negative LDOs. So most LDOs are positive output. So you take a higher positive voltage, like 12 volts, you convert it down to whatever, 3.3, 5 down to 1.8, that sort of thing. But there's also LDOs that are designed to work on the negative side. So like you could, if you wanted to for some reason, use a 12 volt reference for your circuit and then make a rails referenced kind of backwards and upside down. And I'm guessing those negative regulators would be a good reference for building something like this. But unfortunately, I didn't do that. I just went for it. Because they had to solve a lot of these problems, right? For an LDO, you don't know what your load level is. They had to solve that problem. Okay. I've added a lot of caps. like a lot. I think I've added 1,300 picofarads. So the thing that this is starting to mess with is the phase margin. Oh no. Okay. There we go. So it's like you can add enough capacitance where it'll just rail to rail. What is even happening here? Oh, I don't like that. What is that? That's a new type of noise we haven't seen before. Oh. One of those set points it did not like. Yeah, that's real bad. That is real bad. Yeah. So, yeah, more capacitance, not always more better. Yes, diodes can handle reverse voltage. Oh man, I feel like I'm just playing around at this point, but it sure is fun. Yeah, I will crank this up. I just want to run it through the voltage range. But this is the most bizarre thing, is like, even though this is an absolutely awful circuit, it is terrible, it still kind of works, which is weird. I don't like it. Makes me very uncomfortable. Yeah, it's I've heard it said many different ways, but the way I like to say it most is like not letting great get in the way of good enough. It's really weird. This is not good enough. This is too far on the bad side of the spectrum. But there is some middle ground where it would work. Okay, I want to find one of those resistors. We'll add it in parallel. I seem to have misplaced my through-hole components. Let's see. I'm guessing 200 ohms. We'll start there. We'll start with 200 ohms. That sounds like a good starting point. Oh no, was I not showing the oscilloscope for that? Yeah. So, I mean, these systems can be voltage controlled, but I really don't think they should be voltage controlled, because LEDs are inherently current controlled devices. So when you control them with a duty cycle, their color accuracy is preserved. When you control them with constant current or current control, their intensity is more directly proportional to current than voltage, so it kind of works out. And yeah, if you go the other way, it just doesn't work. Yeah. Oh. Very cool. Yeah, I don't know. Do you guys have any other thoughts? I'm going to do the resistor in parallel. Other than that, I'm running out of ideas, and I'd say this stream went pretty well as far as AV setup issues. Internet seems good. So I am very much looking forward to getting back in the rhythm of streaming more often. Hopefully we can figure out... Wait. No, I needed a resistor to not to ground. I needed a resistor from 12 volts. That's what I needed. No. But yeah, there's a whole lot more that can and will be done. But yeah, I'm excited for some of our next projects. We've got a whole bunch of stuff going on. Got a lot of really exciting, projects and ideas coming down the pipe. So yeah, it'll be good. I don't know exactly what it'll be, but it'll be good and it'll be fun, and I'm looking forward to it. We've got a running list of ideas. We've gotten so many great ideas from other people. Other people are great at ideas, I've learned. So yeah, just try to... Oh, there we go. So now I've gone and goofed it up because, oh no, it's just so sensitive. Okay. So now it's still super unstable, but that's because we did something ridiculous. I'm going to take off all of the capacitors except for the 100 picofarad. I think it'll look a lot better. What? Hello? Wake up. Boy, yeah. Choking on my coffee. Yeah, it's a great question, WTP Gaming. Why analog LEDs? Why not digital? So I'll be bold. I'll risk being wrong here. But my understanding is that NeoPixels are not ridiculously expensive, but measurably more expensive than their simple analog counterparts. And there's also the matter of, so you mentioned that your NeoPixel driver was wireless. Assuming it was like fancy wireless and not, sketchy wireless, it's probably able. Sorry, clicked the wrong button. What was I saying? I was saying something. That's what I get for leaning on my keyboard. Yeah. I don't know. They just kind of asked me to. Oh, sorry. Yeah. So what I was saying is, when you have an internet connection, you can then receive ArtNet, so you're not limited to one DMX address, and you just kind of run out of address space really fast with addressable LEDs. And like there'd be hacky ways around that, but like each pixel kind of becomes its own thing. Some controllers, not a problem. They can just handle that. They can handle 3,000 channels. Others can't. So it's, I don't know. Sometimes it's better, sometimes it's worse. Oh no, what have I done? Hello? Did I like break that cap? What is happening? Why is it flashing? Okay, so I'm going over that space that used to be super oscillatory. And it is, oh no, that's negative. One moment. I'm going over that space that used to be super oscillatory. And I do believe that is significantly reduced amplitude. Someone will have to wind back in the stream and check. But I do believe that is significantly reduced amplitude, and we're burning a resistor, which is always cool. That resistor burning smell is very distinct. Very recognizable. So I don't know. It was just kind of didn't really have the DMX channels, and they didn't want it. They already had analog tape. And it was, yeah, I wish I had a better reason. That's really about it. Oh. Yeah, I suppose. Yeah, alright. Cool stuff. So WTP Gaming says, I meant driving the addressable LEDs all the same color. Yeah, I suppose. But if you're driving all the LEDs the same color, I mean, that's like the limitation of the analog ones. I don't know. And I suppose there's 12 volt addressable ones too. Yeah, I guess there's no real reason to pick one or the other, but whatever's cheaper, more available, easier to drive for you. Yeah, it's a good, fair question. I don't have a good reason. Yeah, so Tanner, also a great question. So brand new to DMX. So cool. We've released a couple videos. If you want to learn more about DMX, I think I put the playlist in the description. But I'll try to give you the 1,000-foot view now, without a promise of it being a good 1,000-foot view. Yeah. Okay, that is getting... Oh, yeah! Why did I touch that? I knew it was hot. Literally, why did I do that? That was a terrible idea. Okay. We're just going to turn that off. So do they normally have duty cycle control over the mux? Yes. So usually, I do have my adapter cable. Usually, they receive RS-485 commands. That's usually how these work. So in this case, I have a whole bunch of adapters, but basically have a... starts with a... For me, I'm just using a normal PC, so it starts with a USB to a... that's not a DMX connector. So this is a... It's electrically DMX, so RS-45 traffic, but they use the XLR connector, the XLR3 connector instead of the 5-pin, which is not correct. But thankfully, a lot of people do that, despite it not being in the standard. So they have these cool off-the-shelf adapters that go from the DMX, the not DMX connector, though there isn't really one, to the Ethernet based, or the 6P6C based connector. So then now you have your RS-45 traffic coming on an Ethernet cable, and we plug that in right here. And then so it has an address space, so with these jumpers, a person can set the address they would like, and it'll basically send, I'll oversimplify it, basically sends an address between 1 and 256, and then it sends a value between 0 and 255, and then each of those is called a channel. So in this case, I have, like WTP Gaming said, literally an Arduino, or an Arduino compatible, on the circuit board that is communicating with those DACs, and then all that good stuff. One DMX channel, so one address is assigned to red, green, blue, white, and then you have a DMX controller software. I've been using a really, really basic one. It's just called Freestyler for checking this out, for testing it. The guy I'm helping out has a ETC, I think it's Electronic Theater Controls brand, lightboard, and so he's got more advanced dimming and control and whatnot. So it's basically serial communication brought in. Arduino does stuff, and then, yeah, grabs the channel, lights up an LED. So there's 4 independent strips. You can set them to 4 different colors, 4 different brightnesses, whatever you want. And, yeah, it's generally how it works, 1,000-foot view. So duty cycle control is how some boards work. So I designed a board that we're going to talk about at a future time that does that control, the PWM control. This one does, well, attempts to do analog dimming and fails spectacularly by being marginally stable, depending on the load and the temperature and the day and a lot of other factors that are not easily controlled. Very cool. Well, I think that is unfortunately about all we have for today. How long have we been streaming? I don't have a good timer. Have we been going for a while? Let's see. Viewer activity? No, that's not right. Yeah, I have no idea. How long have we been going? Like an hour? 2 hours? I don't even know. But either way, really appreciate you guys watching today. It was a lot of fun, and I look forward to streaming soon. Next time, we'll have a more celebratory stream. This one was kind of sad, because it's like, I already knew it was not great circuitry. This one's better. I mean, still not super compact or whatever, but, you know, I wasn't really space constrained, so why take 3 months to cram it into a tiny box when you can do it in an afternoon and then take 3 months to publish the video. Oh, anyways, we got lots of cool projects coming up on EE for everyone. Yeah, really just stepping back into it and looking at what we're doing, what we want to do, looking at how we want to strive to share knowledge and and generally bring to life electrical engineering, you know, bringing textbook examples that many people wouldn't bother to really build and actually physically building them, so we can probe them with an oscilloscope, talk about hands-on lab skills and things like that, just general engineering principles that are really awesome. So yeah, I'm really excited to dig into that and double down on that mission while still building huge and awesome and cool projects. So we're going to have some cool stuff coming up in our future videos. I know that for sure, and can't wait to share it with you. Also, the Community Edition electronic load is one step closer. Yeah, it's a really cool thing, so hopefully we'll get that properly open sourced once it's not awful. But yeah, probably have a little bit more tinkering with that at some point in the distant future with some other stuff. Just want to do a new project. You know, we've been playing with inverters and electronic loads forever, and it'll be fun to dig into something else for sure. 1 hour 45. Well, that's not too bad. That's not too bad. Very cool. Well, yeah, thanks to all of you who have subscribed, those that watch our videos, or if you're here for the first time, welcome. It's a cool place to be if you like engineering, or you're interested in learning more about what those weird electrical guys do in the room down the hall. Either way, it was great hanging out with you this morning. And I really appreciate you guys' support and viewership. It's always great to see some regulars. Hey, Eric Johnson. Welcome. Set intensity control, implement current mirrors, or do you know what method? So yeah, for this board, it is doing, I'll just say what it tries to do. It tries to do voltage control. So it's basically regulating voltage on the cathode of each LED. And I went on about this for a while before. So it's awful for color accuracy because the forward voltages of different LEDs is different. So if you set all of the channels to the same voltage, you'll get very different brightnesses. So yeah, this one's not good. So usually you'd want a duty cycle or a current control. But yeah, a current mirror would be one great way to do that. Yeah. Current mirror would be a great way to do that. This one's just basically an op-amp regulating the voltage on the collector of an NPN transistor, which happens to be tied to the LED strip. So not good. Don't do. But it technically lights it up and turns it off, and one could theoretically color calibrate the DMX range to maximize what you're using. However, you'll start to lose your dynamic range. So if you're skewing your curve like one, well, whatever, you can imagine, one increment of your 512 values, one increment of your 8-bit number could mean a larger or smaller brightness step. Whereas with simple PWM, you're getting exactly a percentage of the brightness. Right on. Well, I'll see you guys in the next stream. Thanks for coming in today. Hanging out in the shop. It's always good. See you in the next one. Hope you learned something great today. Or if not, at least you had fun. Bye. Well, I don't have a goodbye slide, so